All right, strap yourselves in because today we're diving deep, deep into black holes. I mean, you've heard all the buzz, right? Seen the pictures, maybe caught a documentary here or there. But have you ever really sat down and thought what it would be like to actually fall into one? To experience it? Just picture it, that vastness of space, that pull, that point of no return.
I think what's so captivating about black holes is that it's not just science fiction, you know? Black holes are actually out there, and the possibility of falling into one is something that really pushes the limits of physics.
It's a journey, really, that brings up so many questions like, what would it feel like? What's on the other side of that point of no return? Well, today, we'll explore spaghettification together. And yeah, it's as terrifying as it sounds, but we'll also try to figure out, at least in theory, what awaits on the other side.
Yeah, so let's start by setting the scene, right? Imagine you're just floating through space, surrounded by this silent expanse, all these stars, weightless, completely alone, and then you see it, a black hole. Massive. I mean, really, beyond comprehension.
And that pull that everyone talks about, is it this immediate crushing force, or does it start subtly?
It actually starts subtly. You'd feel this sense of weightlessness at first, almost like you're in free fall. But as you get closer, that gentle pull becomes this intense acceleration, and you find yourself hurtling towards this point of no escape, the event horizon.
Okay, so the event horizon, it's not a physical barrier, is it?
Exactly. It's more like a boundary in space-time. Once you cross it, the black hole's gravity is so strong that nothing, not even light, can escape. There's just no turning back. It's like going over a waterfall. That current just pulls you inevitably towards the singularity at the heart of the black hole.
And that brings us to, I guess, the spaghettification part. We're being pulled towards this singularity, and it sounds pretty intense, to say the least. What would that actually feel like?
Okay, so imagine the force of gravity pulling so much harder on your feet than on your head. That difference, you know, those tidal forces, are so extreme near a black hole that they literally stretch you, elongate you, like, you know, a piece of spaghetti.
So I'm being stretched, but what about my consciousness? It's still there, right? What does that even mean for the concept of self as you approach the singularity?
Well, that's where things get really complex. You have your physical body undergoing this unimaginable transformation, but theoretically, your consciousness, it would remain intact. And it raises some profound questions about the relationship between, you know, our physical form and our sense of self.
Okay, so I'm stretched, I'm approaching the singularity, but what about someone watching all of this from a distance? What would they see?
That's where things get even more mind-bending. From the perspective of someone watching from afar, you wouldn't actually see someone fall into a black hole. They would appear to freeze at the event horizon. Their image would slowly fade away as time slows down for them relative to you. This is what's known as time dilation. It's one of the mind-boggling consequences of Einstein's theory of relativity. As you approach a black hole, time itself slows down relative to an observer farther away.
So to be clear, I'm frozen in time, stretched out like spaghetti, but somehow conscious. And to everyone else, it looks like I've vanished.
Yeah, that's essentially the current understanding. It's a lot to wrap your head around, but it really shows just how profoundly black holes can challenge our everyday perception of reality.
Okay, so we've crossed this event horizon. We're heading toward the singularity, where, as you said, the laws of physics break down. But you mentioned earlier that our current understanding of physics breaks down at the singularity. Does that mean everything just vanishes?
That's actually what physicists thought for a long time, but there's been a shift in thinking, fueled by some really fascinating theoretical work like the holographic principle.
Hold on, holographic principle sounds like something straight out of a science fiction movie.
It might sound like science fiction, but it's a serious area of study in theoretical physics. The holographic principle suggests that all the information about a three-dimensional object could be encoded on a two-dimensional surface, like a hologram.
So instead of being destroyed at the singularity, our information is preserved on the event horizon, like some sort of cosmic hard drive.
That's one way to visualize it, yeah. Think of it this way. Imagine your entire existence, all your memories, all your experiences encoded on the surface of a black hole. That's the basic idea behind the holographic principle.
Wait, so you're saying falling into a black hole might not be the end?
It's a possibility. Some physicists speculate that instead of being destroyed through a shortcut in space-time.
So it's like taking the cosmic express lane
Yeah.
and skipping all the traffic.
Exactly. But the problem is, wormholes are still purely hypothetical. We haven't actually observed them directly. And there are some pretty major theoretical challenges to their existence.
So wormholes are still in the realm of science fiction, at least for now. But is there any connection between them and black holes?
While some theoretical models do suggest that the extreme curvature of space-time around a black hole, it could create a tunnel connecting to another point in space-time, potentially even another universe. So instead of being the end of the line, a black hole could be a portal to somewhere else entirely.
That's a fascinating possibility, but it sounds like we're really pushing the boundaries of theoretical physics here. How does all of this align with our current understanding of the laws of physics?
Well, that's the exciting part. It challenges our current understanding and forces us to consider new possibilities. It's important to emphasize that these theories are highly speculative. But that's what makes studying black holes so compelling. They force us to expand our thinking, question our assumptions, and just embrace the vastness of the unknown.
I feel like the more we learn about black holes, the more questions we have. Is there anything that stood out to you, the listener, about what we've discussed so far? What sparked your curiosity?
It really is a journey into the heart of mystery, isn't it? A quest to understand the most extreme and fascinating objects in the cosmos.
Okay, so we've covered spaghettification, time dilation, the holographic principle, even touched on wormholes. But there's one more mind-blowing concept I want to explore before we wrap things up. So we've been talking about the possibility of information surviving a fall into a black hole. But what does that actually mean? What kind of information are we talking about here?
Well, that's a really fascinating question, and it leads us to the concept of entropy. Now, you've probably heard of entropy as like a measure of disorder or randomness, right? But in information theory, it takes on a whole new meaning. It becomes a measure of how much information a system can actually hold.
Okay, so the more entropy a system has, the more information it can store.
Exactly. And get this, black holes, they have the highest entropy of any known object in the entire universe. They're like these cosmic information sponges. They just absorb everything that falls into them, and as they do that, they increase their entropy.
So if black holes are these massive information repositories, what happens to that information? Is it just scrambled up, lost forever?
Well, that's where things get even more mind-bending. Some physicists have actually proposed this idea called black hole complementarity, and it suggests that information is both lost and preserved. It depends on your perspective.
Hold on, how can information be both lost and preserved? That sounds like a paradox.
It is a paradox, and it's one of the biggest mysteries in physics. See, from the perspective of someone falling into a black hole, their information, it appears to be destroyed at the singularity. But from the perspective of an outside observer, that information is encoded on the event horizon and it never really disappears.
So is it fair to say it's like two sides of the same coin? Two different ways of looking at the same reality?
That's a great way to put it. It's similar to the thought experiment of Schrodinger's cat, where the cat is both alive and dead until you open the box and observe it. With black holes, the information is both lost and preserved until you choose a perspective from which to observe it.
We've covered some really complex concepts in this deep dive. Information that's both lost and preserved, black holes as these huge cosmic information sponges, and even the possibility of consciousness surviving a fall into a black hole. What implications does all of this have for the search for extraterrestrial life?
Well, it suggests that information might be a fundamental aspect of reality, just as fundamental as matter and energy. If that's true, it could completely change how we search for life beyond Earth. It could mean that life, or at least the information that makes up life, could exist in forms and places we never even imagined.
So we're not just talking about physics here, we're talking about the nature of existence, the very essence of who we are.
Absolutely. Black holes, they're pushing us to rethink our assumptions about reality, about consciousness, about the nature of information itself. They're forcing us to confront questions that have puzzled philosophers and scientists for centuries.
Perhaps black holes aren't the end, but rather a doorway to something new. Something beyond our current comprehension.
And this entire deep dive brings us to a final, fascinating thought for you, the listener, to ponder. If black holes truly are these cosmic information repositories, what does that mean for the ultimate fate of the universe? Could the information absorbed by black holes eventually be...
And even touched upon the possibility of wormholes and other dimensions.
It's been a journey to the very edge of our understanding, and hopefully it's left you, the listener, with a sense of wonder and a desire to explore these mysteries even further.